Hey, and welcome back to Win Biology. Today we're going to study pedigree analysis on X-linked disorders or sex-linked traits. It tends to affect males disproportionately because boys are XY, and because they only have one copy of the X chromosome. If they end up with one bad allele, that means they end up with the disease or the disorder. So there's plenty of different types of traits like this. For example, color blindness, we studied in part 1. Alexei Nikolaevich, the heir apparent to the Russian throne, he had hemophilia. So these are examples of X-linked traits. Today we're going to look at DMD, or Duchenne's muscular dystrophy, where there are several symptoms and signs of this disorder, where a child, usually a boy, will be extremely fatigued. They'll have muscle weakness, really poor development of their cardiac system, and we're going to study how the genes are passed on from generation to generation by looking at the pedigrees. So before we hop into this problem, there's just a few things you have to understand. So there's a few scenarios for boys. So if you're a boy, you're going to always be XY with your chromosomes, but because this is an X-linked recessive trait, there are two possibilities. So you can have a boy who is unaffected and healthy, so he won't have DMD, Duchenne's muscular dystrophy. And on the flip side, you can have a boy who is X to the little d. He has the recessive allele, and this would mean he is affected. So he's got the disease or the disorder. So just those two possibilities. For girls, there are going to be three possibilities, and we'll explain each one. So you can have a normal, healthy, unaffected girl, so X to the big D, X to the big D. So she does not carry the disease or the disorder at all. The other possibility is X to the big D, X to the little d. She would also be unaffected because she's got two copies of the X chromosome, so she would only be a carrier in this case. Okay, it's not so bad. She won't display any symptoms or signs of this disease, but she is a carrier. And the other one, the last possibility, is an affected girl, where she has two copies of the recessive allele. So here's the problem. It says the pedigree below tracks Duchenne's muscular dystrophy, DMD, through several generations. DMD is an X-linked recessive trait. And it says, based on the pedigree, which of the following is true? So we're going to have to go through and we're going to have to analyze each one of these until we find an answer that looks pretty good. So let's go through each one of these choices, A through D. We're going to look at A first. So A is saying, if individuals 2-4 and 2-5 have a fourth child, there is a 50% chance that it will not have DMD. So I've boxed the people in question. That's the couple over there, 2-4 and 2-5. And let's see if this is true. So you've got a male who is affected. He's shaded in, so this is someone with DMD. And his wife is also affected. And we're going to fill in their genotypes here. So the husband is going to be X to the little d, and then chromosome Y. And then the woman here will have XD, XD, both little d. And we're going to draw a Punnett square for this one. And we're going to see what the probabilities will be for each of the offspring. You can see that all of their children actually have Duchenne's muscular dystrophy, and you're going to see why in just a moment. Okay, so we're going to fill in the Punnett squares here, okay, where the letters intersect. Just make sure you write them down completely. Okay, this is X-linked, so that means the Y chromosome will not have anything on it. But now when you analyze it, you can see that all the offspring are little d. They all have the recessive alleles, and they're homozygous for it if they're a girl. So in this case, if you have a man and a woman who both have Duchenne's muscular dystrophy, that means 100% of your offspring will always have this disorder. There's no getting around this. Okay, so that means choice A is false. Choice B, individual 2-1 is a carrier for DMD. This is it. This is an unaffected male, so that's an incorrect choice. There's no way he's a carrier because he's a male. Choice C. Individual 2-3 has a genotype of X big D and then Y. So this is a male and he's affected. So there's no way that he can have a dominant big D allele right there, okay? Because this person is afflicted or affected with this disorder. So that person is going to be X little d and then Y because he is affected. You can see that his box is shaded in. And he's an affected male. So by process of elimination, choice D is going to be correct. So it's saying if individual 3-1, that person there in purple, marries an unaffected non-carrier female, none of their offspring will have DMD. And let's just confirm by doing a Punnett square here. I'm going to go ahead and erase that so that's out of the way. And here's our Punnett square. So individual 3-1 is male and he's unaffected. So he's going to be an XY male and he's going to have a big D on his letter X chromosome right there because he's unaffected, he's healthy, he's normal, does not have the disease. And this is a non-carrier female, so we're going to assign her X big D, X big D. There's no recessive allele in this one. Both partners are healthy, and you could see that all of the offspring are going to be healthy and not have this disease. They all have the dominant allele. So none of their offspring will have DMD, and that's been confirmed right there with the Punnett square. So choice D is correct. That is the only true statement. Problem number 2. Once again, we're going to look at Duchenne's muscular dystrophy, DMD. It's X-linked recessive, which we already discussed. It's only found on the X chromosome. If individuals 1-1 and 1-2 had another son, what is the chance that he would have DMD? So we're going to have to make some inferences, almost like educated guesses. We have to figure out what the genotypes of the parents are. And already, I know that this man here is going to be X big D and then Y because he's unaffected. His box is not shaded in. His wife, however, has DMD, so she's going to be X little d, X little d. She's got the disease. And we're going to do a Punnett square to see the probabilities of the offspring. So we could see that both of their sons already have the disorder. Okay, we're going to fill in the husband here. And this is his wife in generation 1. And let's just quickly do the cross. Okay, so we would see that all girls are going to be carriers for the disease. And the boys are all going to have the disease because it's recessive and it's X-linked. So the chances that the next son would have this disorder is going to be 100%. You can't get around this because, again, if you're a boy, you're an XY chromosome, and if you have one bad allele, that means you're going to have the disease. The girls, on the other hand, so any daughters that they have, they would all be carriers. They wouldn't have the disease, they wouldn't display it as a phenotype, but genotypically, the females would all be carriers, and you could see that individual 2-3 and 2-4 here have the disease, and their sister, that one right there with the arrow, she is going to be a carrier for Duchenne's muscular dystrophy. She's unaffected, but she does carry one copy of the bad allele. Alright, last problem. What is the genotype of individual 2-2? So that would be generation 2. The second person over is this woman here that we highlighted in red. And we're going to look at her sons, and that's going to provide us with a lot of clues. So she has a son who is affected, so he's got DMD. and a son who is normal and healthy. So those will provide us with a lot of clues later on. We're also going to look at her husband, this individual here. He's unaffected, so we know what his genotype will be because this is an X-linked recessive trait. So I know for sure that this man here has the genotype X, big D, and Y. The woman, on the other hand, there are a few possibilities. We're going to say that this woman is normal, and we're going to see that this is an impossible scenario because after you look at the Punnett squares, you would see that 100% of the children would be normal, healthy, and unaffected. And this is impossible because she gave birth to a male. She had a son who actually had this disorder, individual 3-3, that person right there. So in this scenario where she is X big D, X big D, this is impossible. So we can narrow out and we can eliminate that choice. Choice A, on the other hand, X little d y, wouldn't make any sense at all because XY is male. So that leaves us with two choices here. Choice C and D. Choice D we can eliminate right away because she is unaffected. So that leaves us with one more opening, and that is she's a carrier for the disease, which would make sense because she had a normal boy and an affected son. So let's play out the scenario again, where the husband is normal, but now she's a carrier, and I'm going to fill in the Punnett square, and we're going to analyze this. Okay, so if you strictly just look at the boys, it would make a lot of sense. Okay, this right here represents individual 3-1. He's normal, and this Punnett square over here, this lower right quadrant, this is individual 3-3. This is the son that she gave birth to who has the disorder, who has DMD. So this would tell us that this woman is actually a carrier for this disease. So over the course of this 3-part series, you've learned that X-linked disorders or sex-linked traits tend to disproportionately affect males because males are XY. They only have one chromosome, one copy of the X chromosome. So if they end up with a copy of the bad allele, they end up getting the disease or the disorder. So things like Duchenne's muscular dystrophy, color blindness, and hemophilia tend to affect males more than girls. Girls, on the other hand, have two copies of the X chromosome, so they can offset having a bad copy with a good copy of the gene. So it's very rare for a woman to have a disease that is X-linked, because that would mean they need two copies of the recessive allele. So generally this happens when an affected man and an affected woman end up meeting each other, and they give birth to a daughter who would then have the disease. So it takes two parents to both have the disease for this to occur. So I hope that made a lot of sense. If you're having trouble, just go back and watch parts 1, 2, and 3 all over again. You can always put me on repeat. Thanks for watching, and I'll see you next time on Win Biology.